just wait a few more minutes. Oh, actually, we'll just remember the key important things. So yeah, welcome to what is the fourth CONEXS webinar. Just so these are our monthly events, and just for your information, the YouTube channel where all of these videos are based on. So if you want to go back and see any of the previous webinars, or go and see some of the talks that were at our conference that was last month, then many of the talks are on there. So hopefully as time goes on, this becomes a more and more useful resource. So today it's a great pleasure to introduce Dr. Chris Milne from the European XFEL. So Chris did his PhD with Dwayne Miller in Toronto a long time ago, and then he moved to the EPFL and worked for Majid Chirgi, where looked at time-resolved X-ray spectroscopy and did a huge amount of work in that area, before then transferring over to the Swiss free electron laser, and then more recently to the European X-ray free electron laser. So yeah, he has a wealth of experience in time-resolved X-ray spectroscopy, and it's going to be really interesting to hear his talk. So yeah, take it away, Chris.
Thank you very much, Tom. It's a pleasure to be here. And thanks again to you and Faye for organizing this excellent webinar series, and the CONEXS framework in general, I think is really wonderful. So, hi everybody, I'm Chris, and I'm going to talk to you a little bit about ultrafast X-ray science with a focus on X-ray free electron lasers, obviously. And I'm currently as of a few months anyway, at the European XFEL, and I'm the group leader of the femtosecond X-ray experiments instrument, which is one of 6 going on 7 instruments available for user experiments at the European XFEL. And so with that, I'm going to borrow the royal we here and ask, what are we interested in? And you already probably have a pretty good idea of what I'm going to talk about. But what we're often interested in is how things work, right? So a lot of the science that we do is we have a question and we want to understand how something happens or predict something that happens, and then try to figure out whether we're right or not. And a lot of this, for a lot of science, comes down to structure. So what is the structure of something on a macroscopic, microscopic, nanoscopic scale? And you can see here the structure of the hemoglobin protein. And so this is the oxygen transport protein in your blood, and it carries oxygen from your lungs to your extremities and keeps you alive. And it can bind small molecules, and if it's working well, it binds O2, but it can also bind other things like cyanide or nitrous oxide. And here we have a very nice crystal structure measurement of this protein. So we know the position of the atoms to within less than an angstrom. And you can see now the porphyrin rings with the iron 2+ that actually binds the oxygen. So we sort of know everything about the structure of this thing. But as is obvious, the picture of it doesn't really convey a lot of information. So we'd like to see it function. And so then this brings in the idea of dynamics and timescales. And so how do things work, and on what timescales do they evolve? And we have a number of tools that can do structure or dynamics. So we can use X-rays to measure the crystal structure of something, or we can do electron diffraction measurements as well, or NMR. And with dynamics, we do a lot of optical measurements. So ultrafast lasers or femtosecond lasers have been around for quite a while. We can do dynamics with NMR down to, say, millisecond timescales. And what I've got here on the right-hand side is actually an MD simulation from Brian Space on the myoglobin protein. And myoglobin is also a small molecule transport protein in your muscles. And you can think of hemoglobin as being built up of 4 myoglobin subunits. Now, in this simulation, you can see it's a little bit more sophisticated. There's water molecules. You can see, again, this porphyrin ring, or this heme at the center of the protein. But because it's a simulation, we can bring it to life. And so now suddenly the whole picture breathes and becomes alive. And we can see the waters moving, we can see the alpha helices vibrating, we can see the modes of the porphyrin ring. And suddenly this, this static structure that we have on the left turns into something that we can grasp a little bit more firmly and understand potentially how it works. And so the obvious thing here is that we want both structure and dynamics. And X-rays happen to be a powerful tool to probe structure. And very recently, with the advent of XFELs, they've also been capable of probing very, very fast dynamics. Now, many of you are familiar with dynamics on some time scales. For those of you who have modern mobile phones, you'll know that your camera can even do these slow motion tricks where you can catch, water droplets flying through the air, or, Usain Bolt sprinting. And so this is often on the order of milliseconds. And this is kind of the range of electronics usually. You can get down to faster, the microsecond regime. This is where, for example, hemoglobin goes from relaxed to tense. So when it binds and unbinds oxygen molecules. This is also the time scale of phosphorescence, so anything that glows. We move down into the sort of faster time regime, the nanoseconds. This is where very fast, electronics work, computer processors, for example. Picoseconds gets into molecular motion, so translations and rotations. Femtosecond starts to become the nuclear motion, for example, the symmetric stretch in water. So the period of these protons moving away from the oxygen is about 10 femtoseconds. And the isomerization of the retinal protein in your eye that allows you to see. So when this long organic chain absorbs a photon, it isomerizes around a carbon bond here. And this happens on the order of 200 femtoseconds. So it's one of, if not the fastest biological process that we know of. And then you can move into the timescale of electron dynamics. And this is the femtosecond regime, or even the sub-femtosecond regime, where the motion of an electron can be on the order of attoseconds. And you have a range of tools at your disposal to probe these different timescales. And what I've got here at the top are the X-ray sources that are sort of available, depending on what process you'd like to look at. So this includes synchrotrons, which you've heard a lot of through the CONEXS meetings. We have X-ray free electron lasers, which I'll talk a little bit about. Laser plasma sources have been around for a while, and they produce bursts of hard X-rays. And you can also do some tricks at accelerators to make short pulses, either by slicing the electron bunch with an optical laser, or by creating so-called crowd cavities, where you can then make it so that at certain regions of the ring, the electron bunch duration is quite short. Now, the question you might ask is, we have these very fast things, but we have to detect them somehow. And so how do we detect fast things? And it turns out we're just going to use methods that have been around since the advent of photography, which is that we have a slow detector, in this case, a camera film, and we're going to use a brief flash of light to image it. And so the photographic film is not inherently able to see the bullet going through the grapefruit, but the flash of light, if it's short enough, can capture this event. And so this means that we can use slow detectors to measure fast things. And so we're going to do exactly that. The other thing that short X-ray pulses can do is they only interact with your sample for the duration of the pulse. So if the pulse is, say, 100 femtoseconds long, the X-rays only interact with your sample, whatever it is, for 100 femtoseconds. And 100 femtoseconds is fast. So a lot of dynamics can't occur that quickly, which means that with this very short pulse, we can freeze certain things in place. And so this is an example of a simulation from Richard Neutze and János Hajdú, where they take a single protein and they deposit into it the energy you would deposit into it when you hit it with a certain number of X-ray photons. And then you can see that the protein and the atoms in the protein basically don't move or don't start to become disordered until you get to sort of on the tens of femtoseconds time scale. This can also be applied to things like crystals, where your periodic lattice will only be damaged in the time scale of the motion of the atoms, which is, say, on the order of some tens to hundreds of femtoseconds. So this means that short X-ray pulses can be very good imaging tools. you will destroy your sample, but the measurement that you make from your sample while the short pulse scatters off of it, that would be an unperturbed, undamaged measurement. Okay, so you all are very familiar with the different kinds of X-ray techniques one would have available. But just to remind you, you can use almost any X-ray technique you can think of. There are some limitations, obviously, to the fact that maybe with a short X-ray pulse, you're either depositing a lot of energy very quickly into the sample, or you're creating a lot of photoelectrons in a very short period of time. But in general, here are some examples. We've got on the bottom left here, elastic X-ray diffuse scattering. And this is where you have a crystal and you scatter your X-rays off of it. And then you can measure the diffuse scattering peaks between the Bragg peaks, which probe different parts of the Brillouin zone. On the top right, you've got resonant X-ray diffraction. And this is where you tune your incident X-ray beam close to a resonance. So say around an absorption edge in your sample, and then you scatter off the crystal, but you have some electronic sensitivity to the resonance you're close to. And then on the bottom right, you have straightforward Bragg X-ray diffraction, where you have a periodic lattice, you non-resonantly scatter off of the lattice, and you measure the diffraction peak. And I've included here in this blue box, unfortunately my cursor's disappeared on me, so I can't indicate it to you, but you can also do these tricks off of any kind of crystal. And so one of the methods, which I won't talk too much about, but which has become one of the more interesting methods available at XFELs, has been so-called serial femtosecond protein crystallography, where you shoot your short X-ray pulse off of a stream of protein crystals, and then the X-rays diffract off the protein crystal. And for this, you need, as you might expect, different laser excitation wavelengths. So if you'd like to excite vibrations in your material, you might want infrared. If you'd like to excite phonon modes in your condensed matter crystal, potentially you want terahertz frequencies, so very low frequencies. If you want to excite a chromophore in a protein, maybe you'd like to have UV or visible. So you'd like to have tunability in your pump source. And then for your probe, it depends on which of these techniques you're going to use. But you'd like the reasonably standard ability to make either the monochromatic X-rays or the full bandwidth of the XFEL, which could be some 10 to 50 EV wide, depending on the photon energy. Ideally, you want to have these things be short. So the dynamics you can measure will be determined at least a little bit by how short these pulses are and how well synchronized they are. And so for the dynamics that I'm going to talk about today, these are on the order of perhaps some tens of femtoseconds. Now, you can also do experiments on disordered samples. So this could be a gas phase, gas jet, or this could be a protein in solution. And for this, we can use techniques that you're all very familiar with, like X-ray absorption spectroscopy on the bottom left here, where you want to have a monochromatic X-ray beam, and then you scan your X-ray energy. And then you can measure the pre-edge and the edge position and the near edge and then the X-AFs. And you can extract out then a lot of electronic and structural information from the sample. And then on the top right, if you add, say, a dispersive X-ray emission spectrometer to this, for example, in the von Hamos geometry, you can measure the emission spectrum in parallel with the absorption spectrum. And then you can obtain a so-called resonant X-ray emission measurement, which allows you to obtain more information about the electronic states that are relaxing to fill your core hole. And so this gives you complementary information to the X-ray absorption process. And then you can also do X-ray scattering off of disordered samples like liquids or amorphous systems. And so there's a generic example of this here on the bottom right, where your stream could be neat liquid, it could be a gas jet, it could be droplets, there could be something in the stream, either particles or nanostructures. And all of these things, again, you would like to be able to excite over a range of wavelengths. And the specific application here for spectroscopy is you'd like tunability in monochromatic X-rays. And so depending on what X-ray absorption edge you'd like to look at, then you'd like to be able to reach, the edge that is relevant for your sample. Okay, this is just to remind you that a lot of what I'm going to talk about is based on third generation light sources. And here I've shown you the two methods that are generally used at synchrotrons. We have bending magnets and wigglers and undulators, and these are standard. You know them quite well. The key here is that we're going to be extending this wiggler undulator concept into a much longer extent in order to obtain the X-ray free electron laser photon flux that we need for our experiments. Now, just as a reminder, and this is something that various facilities around the world have put some effort into, you can do time-resolved X-ray measurements with synchrotron, and these are usually limited to on the order of about 100 picosecond time resolution. And obviously, you can do much longer timescale measurements out to, say, microseconds or milliseconds as well. And so these are the sorts of time scales that one might measure at Diamond or at the SLS. Now, if we take our electron source and we accelerate it to a sufficient energy, and then we inject it into an undulator, this will cause this wiggling pattern of our electrons. And each time it wiggles, it emits photons. The photon energy is going to be dependent on the electron beam energy and on the strength of the magnetic field. And so what was developed many years ago was the ability to generate infrared photons using this technique. And so free electron lasers were created. And so they lased in the IR, and they were tunable. And the extension of them into the X-rays happened only about 12 years ago now at LCLS, the LINAC coherent light source at SLAC. And the key there was not only the ability to make quite strong magnetic fields, so in vacuum undulators, but also to have very high electron beam energies, giga electron volt, or several tens of giga electron volt electron beam energies, and also the emittance, so the ability to control the size of this electron beam. And here on the top right, you can see that as these electrons propagate, they emit photons, and they emit incoherently. So the electrons do not know anything about the other electrons, the photons don't know anything about the other photons. However, at a certain point, if enough photons are emitted, the photons start to interact with the electrons. And this creates a feedback, which can lead to gain. And this feedback causes so-called microbunching, which means that there is a fixed phase relationship between these different electron bunches, which then emit coherently and at the same wavelength. And as you propagate along the length of your undulator chain, you get through this so-called gain region and finally into saturation. And saturation in this concept corresponds to when the electrons, the intensity of the photons that are being generated is sufficient to spoil the electrons. In other words, the X-rays are so bright, they start to wreck the phase relationship of the electrons to each other. And on the bottom middle here, you can see the gain curve that LCLS measured. And so they've been operating in the X-ray regime since 2009. Now, a quick perspective on the photons, because these aren't synchrotron photons, they are X-ray free electron laser photons. And so because it's a single pass system, each travel of the electrons through the undulators produces a markedly different pulse characteristic. And this is to the extent that because it's seeded from noise, so the fluctuations essentially of the electron beam energy within the undulators, you get this stochastic nature of the amplification process. And the result is, for example, an X-ray spectrum, such as this video, where you can see that we have these characteristic spikes, which are representative of the SASE process, the self-amplified stimulated emission process. And this means this is what the X-ray spectrum of your X-ray pulse looks like. Obviously, if you put it through a monochromator, the fact that you're getting this energy jitter and these spikes will lead to amplitude jitter in your monochromatic X-ray beam. One of the interesting things is that if you have control knobs on the electron beam energy, you can do things like change the bandwidth of the FEL. And so this is an example at the bottom here from XFEL, where Sven Reiche and his collaborators showed that they could increase the bandwidth of the photon spectrum to 2.5%. So this is centered at about 6 kV. And so this is some hundreds of EVs. And so you do have a bit more control over these photon properties, but you should keep in mind that the spectrum that comes out is not terribly nice compared to, say, a synchrotron spectrum. Now, the pulse energy also varies. And so here you can see a histogram of the pulse energies from LCLS from several years ago. You can see that they're generally grouped around 2 millijoules, which is nice. That's a lot of X-rays per pulse, but the stability of them is not great. And so they can fluctuate in intensity quite a bit, on the order of, say, 30 or 40%, up to 100%, depending on the X-ray free electron laser. The pulse duration and the pulse shape also changes. So if you think of measuring the X-ray pulse in time, which is what these researchers did at the FLASH XFEL, they were able to measure the photon pulse shape. And so what is the structure of this pulse in time? And you can see that it varies a little bit. And so you get these spikes and you get these sort of secondary peaks. And so this means that this is not a uniform pulse in time or in energy. And then you have the inherent issue that because you'd like to do a very fast timing measurement, you want to have good control or the ability to measure the arrival time of this X-ray pulse. And for very fast measurements, this is usually relative to your initial optical pulse. So you shoot your optical pulse at the sample, you excite it, and then you probe it with the X-rays. But to go to the very best time resolution, you'd like to either have control with excellent accuracy of this time delay, or, and this is the approach that many facilities have taken, you simply measure it. And so you can see that on the left here, we have a relative arrival time measurement from the SACLA Japanese XFEL. And you can see that over a period of a few thousand shots, the arrival time of the X-rays relative to the optical laser varied by a few hundred femtoseconds. And a similar measurement was performed at LCLS on the bottom right. And the nice thing is that when you have this kind of diagnostic available to characterize the arrival time, you can then take this information shot to shot, so say at 100 hertz at a low repetition rate facility, and use that then to correct the arrival time. And this correction then allows you to achieve much better time resolution than if you average all of this data together. Now, the pulses that are produced from XFELs are also transversely coherent, so they're spatially coherent. Certain FELs can also produce longitudinal coherence, which means that in time they're coherent as well, but they will all produce spatially coherent pulses. And here you can see an experiment that was done in Japan where they scattered the X-ray beam off of some gold colloids. The scattering allowed them to create different trajectories of the beam onto their detector. And then they created essentially a Young's two-slit experiment where the beams then interfered in the far field. And so here you can see on the right-hand side and on the bottom left, the fringes that could be measured from this, this fact that you have a coherent beam scattering off of these apertures, which then allows you to create these fringe patterns in the far field. And so this is something where it becomes much more similar to an optical laser. And for those of you who've worked with those in the labs, you'll know that when you hit the edge of a mirror, you'll get some fringes from that edge. If you get a speck of dust on it, you'll get a target pattern effect. So it's both a blessing and a curse. It means that the optics for an XFEL become very special because they have to be quite flat and quite smooth, because any imperfection can lead to these sorts of optical interference effects or fringes. Now, this is a sort of a quick blast of XFELs. They're all over the place. They're in Korea. There's one in Trieste, which is a bit unique because it's seeded with an optical laser. There's one in Swissfel, Japan. The one I'm currently working at is actually bridging the gap between Hamburg and Schenefeld. So it jumps between two different states in Germany. There's one being constructed in China. And so these are, let's say, becoming more and more prevalent. And these are all user facilities, which means that you can use them. You write a proposal just as you would at a synchrotron to do an experiment. And then in certain cases, for example, at the European XFEL, you'll even get travel money and accommodation to stay and do the experiment. And so you should think of these just as you would a third generation storage ring. Now, the XFEL where I currently work is a little bit special because it has, it runs 3 experiments at the same time. And so you can see the branches here. We have the so-called SASE-1, SASE-2, and SASE-3 branches. SASE-1 and SASE-2 are hard X-ray. SASE-3 is soft X-ray. And at any given moment, all 3 of them are running, and all 3 of them have users and experiments at them. Now, on the top right here, we actually have the pulse pattern of the European XFEL, which is a little bit unique. It has a burst of several hundred to 1,000 pulses that occurs at about a megahertz repetition rate. And these bursts occur at a 10 hertz repetition rate. So you can think of this as a train of pulses that occurs at 10 hertz. And within this train, they're going to different experiments. And indeed, some of the experiments take advantage of the fact that there's this high repetition rate train of X-ray pulses. Okay, so here's an example of an X-ray instrument. This is a hard X-ray instrument. You will not be surprised to know that the methods used at XFELs are very similar to methods you're familiar with. You can see here, this is a hard X-ray in-air instrument. There are some chambers involved, but the majority of the experiments can be done in air. There's a large detector in line with the beam to measure the scattering. So say wide-angle X-ray scattering patterns. There's a von Hammos dispersive X-ray emission spectrometer, where you can tune a range of Bragg angles and even add multiple detectors to measure multiple emission lines. There's a Johann spectrometer with 5 crystals. And there's some additional components too, which I'll get into later. But you can see that it's sort of a bit of a flexible setup, as you might find at a hard X-ray instrument at a storage ring. Now, some of the sample environments we have are solid state, where you can work in vacuum. And here's an example of a single shot experiment where the researchers were looking at the ultra-fast melting of metallic materials. And the X-ray pulse in this case was destroying the sample. And so a grid of samples was used, and it was raster scanned to a fresh spot each time. On the right is a liquid jet, which some of you may be familiar with, where you have, a chemical or biological sample and you flow it. And in this case, what the figures on the right are showing are what happens when your, say, 4 millijoule X-ray pulse interacts with the jet. And as you might imagine, it perturbs the jet. And so the key is to be able to flow the jet at high enough speed that the next X-ray pulse encounters fresh, unperturbed sample and jet. You need detectors. And so here's an example of 2 different detectors. This detector on the left is called the large pixel detector, and it's actually provided to us from Rutherford Appleton Labs. It has 500 micron pixels, and it can measure up to 400 pulses in this train, which means it's a single pulse capable detector. On the right is an example of some X-ray emission that was measured using a Jungfrau detector from the Paul Scherrer Institute. The Jungfrau is not capable of seeing the pulses in the burst. And so the image that's shown here is an integrated signal of a few hundred pulses that were all acquired during this train. And you can see that you can measure quite nice K alpha, K beta, and even valence to core using this approach. You need a pump probe laser. And so this is a bit special because the pump probe laser should match the repetition rate of the X-rays, meaning it's not a commercial product. It was built for the European XFEL. And you can see that with an OPA, it's tunable from the UV to the infrared. And then, and this is something that is actually a crucial aspect to XFEL experiments, you have to analyze your data. And this is challenging because the stability of the XFEL X-rays and the fact that you collect so many single pulse events means that you can do a lot of data filtering. And so this is an example of some work that Mikola Biednov from FXC has done to help users analyze their pump probe data on a shot-by-shot basis or on an integrated basis for X-ray emission or X-ray scattering measurements. Okay, So let's finish up with some interesting science, shall we? So here's an experiment that was proposed in the very early days of XFEL, the free electron laser at the Paul Scherrer Institute. And the idea was to probe the phosphorus moiety of this copper OLED material. And so this OLED material, which is synthesized by Matthias Voigt from the University of Bremen, is actually a promising candidate for a copper-based OLED. And so, as you will know, OLEDs are showing up in more and more devices. So the last version of the iPhone extended this to the full range. LG TVs have a lock on OLEDs. And these are generally quite nice display technologies in comparison to LEDs. And here you can actually see this copper OLED material when you run some small current through it. And you can see it glow this lovely green color. Now, it turns out that this green color is coming from this excitation process and then so-called thermally activated delayed fluorescence between triplet and singlet excited state. So the green in this image is coming from this relaxation process from the singlet state. And normally this would be short-lived. But because of this thermally activated delayed fluorescence, this triplet, which is long-lived, acts as a reservoir to populate the singlet. And so essentially what happens is you excite it either electronically or by shining light on it. And then there's population transfer to the triplet. And then there's back population transfer as this fluctuates around in temperature. And so what we wanted to see was we wanted to probe the phosphorus moiety of this molecule to understand how it was involved in the charge transfer process of this thermally activated delayed fluorescence in the excited state. So DFT calculations indicated that this triplet excited state had charge transfer character between the copper and the phosphorus, but this was only hypothesized, and we wanted to see if we could measure it. So this experiment was led by Grigory Smolentsov from PSI, and he did some measurements at the copper K-edge. And so he measured the signature of this triplet excited state using X-ray absorption spectroscopy, using a setup at the super-excited beamline at the SLS. And he did this using straightforward X-ray absorption with Matthias's help. And then they brought the sample over to XFEL, and we measured the non-resonant X-ray emission from the phosphorus. And so this is K-alpha-1, K-alpha-2 of phosphorus. And the idea was then to measure the emission using this setup. So we focus our X-rays, we have the optical pump laser onto the jet, and then we use a von Hamos geometry dispersive emission spectrometer to measure in a single acquisition this emission spectrum. The advantage this particular method has at XFELs is that it's non-resonant, which means that you can use all of the photons coming out of your XFEL. And because you're not normalizing to anything, because you're not scanning, you can simply accumulate the emission spectra. And so this was an ideal experiment for, as it turned out, the first experiment we did on a chemical sample at XFEL. And here you can see what happens when you shine your excitation laser onto the jet, and you can see again this lovely green glow. And here on the bottom right, you can see the charge transfer signature from the shift of the K-alpha-1, K-alpha-2 X-ray emission lines that we would expect if we do have this charge transfer excited state character between the copper and the phosphorus. Now you can also do biochemistry in a time-resolved fashion. And so this is an example from the group of Majed Chergui. This was the PhD thesis of Dominique Kinsel. And the idea was to probe myoglobin, but instead of binding, say, oxygen to it, nitric oxide was bound to it. And NO is an interesting system because it's involved in cellular transport in mammals and mussels, and it has peculiar dynamics. And so these dynamics are shown here on the right, and they were measured using optical methods. In this particular instance, resonance Raman. And the reason the resonance Raman is interesting is because what they measured was an intermediate shown here on the right, where we have our NO molecule, and it's bound to the iron in the center of this heme plane, but this heme plane is no longer flat. It's actually slightly puckered down towards the histidine. And no one had seen this before. So generally speaking, the consensus was that the NO was gone, it was away somewhere. This was down, but there was no energy between, or there was no binding energy between these systems. And the recombination then just happened stochastically as the NO came back into the pocket and then interacted with the iron. And what these researchers were able to show was that there was a change in the energy, in the bond energy between the iron and the histidine, which indicated that the NO was actually bound, even though this iron was domed. Now, the interesting thing here is that when you bind and unbind this NO, and when you change the electronic character around the iron, you also change the spin state of it. And so the question that was asked was, first, can we see the structural changes? And also, what is the spin state of these various intermediates? So this experiment was done at 3 different XFELs, European XFEL in Hamburg, SAKLA in Japan, and SwissFEL at the Paul Scherrer Institute. And the goal was, as I mentioned, to measure X-ray emission, absorption, and potentially X-ray scattering to try to understand what was going on when you photoexcite this protein and knock the NO off of the heme. And here you can see some results from the X-ray absorption measurements at SAKLA, where you can see that first that there's a very, very fast change in the signal. So the rise time in the signal here is 110 femtoseconds, which indicate that there's a very significant change that's taking place in this protein after it absorbs a photon. And then if you look on the bottom left, you can see the relaxation processes and the different timescales of them. And each of these can actually be seen in the optical spectroscopy as well. Then X-ray emission measurements were performed, and some of these were performed, as you can see, at almost all of the XFELs. The data that's shown here is the data from the European XFEL and SAKLA, and this is more sensitive to the spin state. And so the X-ray absorption, the assumption was the X-ray absorption should provide information on the structure, and the XES, and specifically the K-beta XES, would potentially give more information on the spin state of the iron atom. And so the summary of this conclusion, which was published in the middle of last year, actually, is that we can see the evolution of these spin states. And so we go from a low spin ground state and then a low spin excited state where the NO is unbound. So it's come off of the iron. And then we move into a high spin state as the iron domes. So as the iron moves towards the histidine, we move into a high spin state. And then we're in a high spin state when the NO rebinds. So this geminate recombination process to the domed iron is also in a high spin state before relaxing back to the low spin ground state. And so the combination of these different spectroscopies allowed both the dynamics and the electronic spin state of the iron to be resolved on ultrafast timescales. Now, we also have the ability to do nonlinear X-ray methods. And so this is more of, let's say, a nascent field, because up until now, we haven't had access to short enough, intense enough X-ray pulses to perform nonlinear X-ray measurements as one might with an optical laser. And so here's an example of an experiment we did several years ago at LCLS, where we set up a dispersive von Hamos X-ray emission spectrometer to measure the K-alpha emission from copper and also from iron. And the data shown here is from copper. And the idea was to come in with an intense, tightly focused X-ray pulse and follow the evolution of 1 photon and 2 photon absorption processes in the metal, and to try to understand the ratios between them, the formation as a function of fluence and also X-ray photon energy, and to see whether or not we could demonstrate that this was a 2 photon process or a 1 photon process. The advantage the dispersive spectrometer gave us is it allowed us to see the formation of the K-alpha emission. And because our incident X-ray beam was below the K-alpha absorption edge, any formation of the K-alpha emission that we could see had to stem from a 2 photon absorption. And so with this, Jakub Szlahetko was able to calculate actually the probability of the two photon absorption process as a function of incident X-ray energy. And this is an interesting topic, because if you imagine that you're shooting your X-rays at a sample and you'd like to look at, say, for example, the crystallography of it, you'd like to avoid absorptive processes if you can, contributing to your signal. And so potentially this would allow you to, by knowing the absorption edges in your sample, to move your photon energies away from possible problems into, for example, two photon absorption processes. You can also extend this in the direction of nonlinear X-ray spectroscopy. Now, this is a field that is very well established in the optical regime. This is a book in the left here from Shaul Mukamel describing the different forms of nonlinear optical spectroscopy and the information content that you can extract. And then on the left here, I've shown an example of a so-called transient grading experiment. In this particular experiment, what happens is we come in with two visible laser pulses with a crossing angle. And these two visible pulses are coherent, meaning that they have been produced with a beam splitter or a grating. And so they have a fixed phase relationship with each other. And so when they cross in the sample, they create fringes, intensity fringes, exactly as in the X-ray scattering experiment from Saklai showed earlier. These fringes then correspond to intensity modulations spatially in the sample. And you can scatter a second beam propagation direction off of these fringes. And so that's the green pulse here. And so what happens is you come in with your two pulses, your two red pulses, and then your green pulse comes in at some later time, scatters off of this intensity modulation. Because it's a grating, you will scatter it into a new, different direction. And this allows you to probe, for example, diffusive energy properties of the material, charge carrier relaxation. And it's also a very sensitive optical spectroscopy technique because it's background free. When the fringes are not induced in the sample, your probe laser pulse does not scatter into the correct direction. And so Chris Svetina, with his collaborators, Christian David and others from XFEL, came up with the idea of trying to generate this grading pattern using X-rays. And so in the middle here on the right, what you actually have is you have an X-ray grating, and there's a zoom in of it on the right-hand side there showing this fringe pattern, and then actually an even further zoomed in image of the grating itself. And when you shoot your X-ray beam through it, it actually creates these different grading orders. And in the near field, these grading orders are not separated, they're overlapping with each other. And this gives you the possibility of putting your sample in at a certain distance from the grating in order to induce intensity fringes in your sample. And so what Chris did was he took several targets, PMMA, so just plastic or gold-coated substrates, and he then exposed them at the calculated distance to get a 189 period grading in his targets away from the X-ray grating. And you can see in the bottom here, we actually have these lovely fringes, and these were permanently written gratings. And so he was able to analyze them offline using a microscope and an AFM. But the neat thing is you can also do this pump probe. And so if you decrease the intensity of your X-ray beams, these intensity modulations in the sample become transient. And these transient gratings can then be probed, for example, using another X-ray beam, or in this case, using an optical beam. And so the experiment was done at the hard X-rays. This was at 7.1 keV, and it was done on BGO, bismuth germanate. And the idea was to create this intensity modulation in these fringes in the sample and then probe them using an optical laser. And on the right-hand side, you can see the quadratic dependence of the pump intensity. In this case, this would be the X-ray intensity. And you can see that this corresponds to then a two-photon process, a nonlinear process in X-ray intensity. And in the middle, you can see the signals that are measured, which clearly show these lovely oscillations. And the Fourier transform of these oscillations corresponds to visualization of the A1 optical phonon at 2.6 terahertz in BGO. And so this is the first demonstration of hard X-ray transient grating. And this can be extended now to liquids. It can be extended to various kinds of solids. And it's a very interesting method, which we're currently on the very beginning of. So with that, I'm happy to conclude. I hope you'll take away that we can do X-ray experiments at XFELs that you'd be very familiar with and comfortable with. The science that we're doing is an extension towards ultrafast dynamics. And with these ultra short pulse durations, we can not only probe very fast events, but we can also do some new kinds of measurements that would not be available with the longer pulses from a synchrotron. These X-ray methods are all complementary to each other. And so you can think of them as giving a different viewpoint on the sample. And what I haven't mentioned here is that there's an awful lot of exciting development going on in fields related to this. And this is where my good friend Tom Penfold comes in, where you can start to think about ultrafast dynamics and how to simulate them, X-ray interaction with matter, quantum chemical simulations. And so XFELs are really just starting off. And we'd be happy if you would come join us and do some experiments with us. Don't hesitate to get in touch with your local XFEL facility. And with that, I'd be happy to answer any questions.
Okay, thanks very much, Chris, for a really great talk. Yeah, as I said at the beginning, if you've got any questions, just dump them in the chat. Either you can either write the question or you can just say you have a question and then I'll ask you to turn your mic on, whichever works out as easiest. So while people type, just a quick, so you showed the nonlinear kind of X-ray spectroscopy stuff. How feasible? So if we went back to the example of your copper complex, how close is it to be able to doing time-resolved nonlinear X-ray spectroscopy where on something like that, where you'd be, at the K edge, you'd be more sensitive to the 3D transition. You'd be blowing up the pre-edge essentially.
So there are researchers in Japan who have actually done exactly that. So what they did was they did a copper K edge X-ray absorption scan with the target of doing 2-photon X-ray absorption. And they saw exactly as you described, which is a sensitivity to different parts of the spectrum that corresponded to the different selection rules of 2 photons versus 1 photon. Now, whether or not you could use this then as a probe technique has yet to be demonstrated. It could certainly be considered. The main thing to remember with these methods, though, is that it often takes significant intensity. Which means that you would need to do, as we did in this experiment, you'd need to move to a fresh spot for every shot. And so you wouldn't want to do this on a very valuable sample. So copper is great.
Yep. Okay. Are there any other questions? Feel free to unmute your mics and ask. Okay. While we give a couple more minutes, if there's any other questions, I've just so I've already put in the chat, which I hope you can all see, the link to the YouTube channel of previous videos and where this recording will go up soon. I'm also putting in the link to the next CONEXS webinar event, which is going to be given by Miriam Garcia Fernandez, which is going to be from Diamond Light Source, which is going to focus on soft X-ray resonant inelastic X-ray scattering. So I think we've had mostly hard X-rays, so we're going to move to X-ray, the soft X-ray regime. Yeah, I hope you'll all be able to join us. And otherwise, that just leaves me to thank Chris again for a really great webinar, and thank everyone for attending, and hopefully see you at the next one.
Thanks again, Tom. It was a pleasure. And thanks to everybody for joining this.